be telling you about not machine learned models, but models that humans make. But I'll try to make close relationships to the kinds of systems that you're studying in this group. So I'm a little bit of an outsider. And this has been work over the last 15 years or so with a wide variety of very talented graduate students and postdocs and colleagues. And we're going to start out in a sort of historical way with the discovery of strange behavior that we find in physical models with many parameters. And then we'll go to a discussion of how differential geometry can tell you information about why these models can be predictive, even though they have so many parameters. And then I will end with a way of taking the parameters in these very messy, complicated models and distilling them into something that looks a little bit like a physical law. So as I understand, the purpose of this conference is to get machines to take things like neural network models, which have millions of parameters rather than hundreds or thousands of parameters the way the physical models have, and to get them to make predictions about the world, but then as the last step, to get those predictions to become comprehensible, not just an oracle that tells you from the sky, this is the answer to your question, yes or no, but a little bit of why. So let me see if I can succeed in this endeavor. So in physics, we have a wide variety of systems that start out very complicated, like collections of atoms interacting via Schrödinger's equation, and end up giving you comprehensible theories of nature, superfluids and insulators and semiconductors. The tradition in physics is to focus on high energy physics, in which you have beautiful, elegant string theories and electroweak symmetry breaking and quantum chromodynamics leading to very complicated behavior. But the model reduction in both of these cases is very similar, that we go from Schrödinger's equation to our theories of the metals and insulators and superfluids and semiconductors in very similar mechanisms. And this is reductionism, basically. And reductionism is not nearly as powerful in systems like biology and even chemistry. But the other technique in physics is to guess the answer, to come up with some elegant, simple model that captures the essence. And the words associated with this are Occam's razor, and for physicists in particular, spherical cows. That we make simplified models. But what I want to emphasize in both cases is you have a very complicated real world, and you end up finding that it behaves simply. And then you'd like to know why it behaves simply, and that's the 3 steps. Why is simplicity coming out of complicated interacting systems, even when you don't have small parameters? And the second step is can we come up with a human comprehensible interpretation of the simple behavior? Now, again, I'd like to make a small connection to the machine learning and deep neural networks that have been so exciting in their ability to take messy systems, throw millions of parameters at them, and get behavior. And the clue here and the tie to my talk is some recent work in deep neural networks, which say that if you make them wide, meaning if you give them many more parameters, weights in the neural connections, then you have data. Then you can generate not only can you train them perfectly, you get perfect recognition of the training set, but you get better generalization the wider the network, the more redundant variables you have, which is the opposite of traditional nonlinear fits. Fits in general tend to get worse if you have more data points, more parameters and data points, then you're fitting all the noise. Here, it gets better and better as you make it wider. And what I'd like to talk about here just for a moment is that it's not that neural networks, all the ways of fitting are better if you make them wide. It's the training process, when it ends, finds a set of neurons that does a good job. And this reminds me very strongly of some early work in disordered systems by Susan Coppersmith and Peter Littlewood, which they called phase organization. And they found very bizarre experiments in charge density waves that they could explain by saying the charge density wave was a nonlinear system that organized itself to a fixed point, that learned something about its environment. And it had lots and lots of metastable states, or stable states, stable fixed points under their training procedure. The experiment was acting as a training procedure. And most of those fixed points were inaccessible. That you would only reach them if you started very close to them. And you can think of it as, in this simple one-dimensional picture, that almost all initial conditions will flow to one of these two edges of this interval. And their analysis explained that there were lots of local regions in this charge density wave, each of which was training in this way, that you would fall to an edge. And then each of those edges formed an edge of a hypercube. And so your distinction is that the well-trained systems, the ones that exhibited this bizarre behavior, were the corners of a hypercube in the state of all possible systems. And the same thing should happen in high-dimensional models where you try to fit the observed behavior. You will typically get stuck at the boundaries of only a small number of states will fall into the interior of this space of possible behaviors. Many of them will get stuck at boundaries, and if you have a high-dimensional manifold, you get stuck at a hypercorner. And what I'm going to tell you today is that the space of possible predictions in nonlinear models, in many human-developed nonlinear models with many parameters, don't form a hypercube, they form a hyperribbon, and I'll tell you about hyperribbons. And that the hyperribbon, the edges of the hyperribbon not only are the ones that often show up when you do nonlinear fits, but also exhibit simpler models. They are the spherical cow, the Occam's razor, the simplest description is compatible with the data. So first of all, I want to talk about parameters. These are the knobs we turn to fit reality. And this is the model that got us started. This is a cancer biology model. You've got signaling molecules that attach to receptors on the membrane, and a bunch of complicated, really messy kind of reactions happen. And then some signal gets sent to the nucleus that causes it to either differentiate or become a neuron. And here are our differential equations. Each of these is a nonlinear differential equation. Each of them have parameters. Here there are 6 unknown parameters in this one equation. There are 48 parameters in this model. And back in the days where we were talking about this seemed just ridiculous. That this was before the field was called systems biology, and I said, too many parameters, this is going to be a mess. And my biology colleague persisted, and we did it. And sure enough, when we finished, we could fit the 63 data points with our 48 parameters, and all the parameters had huge error bars. The best determined parameter in this model had a 5,000% error range. It was unknown to a factor of 50, and it got much worse. Now, we now know from neural networks that you could have millions of parameters and make good predictions. But when we found this, and then we tried to make predictions, we were startled, or I was startled. This is a prediction of the model. This is this same ensemble that generates this giant range of uncertainties in parameters, makes 20% predictions about the behavior on new experiments. And it happens to agree with the experiment. That we did the experiment afterwards. Now, this is possible because these parameters only matter in certain combinations. That is to say, if I take the chi-squared, the deviations between the experiment and the model, and I plot contour plots, the stiffest direction, the direction where the behavior changes fastest, which is some linear combination of multiplicative factors on all the parameters, is much more closely spaced contours than the sloppy directions. Now, you may think that this isn't a very impressive separation, but you haven't noticed that the vertical scale is 1,000 times smaller than the horizontal scale. Okay, I'm going to talk about the eigenvalues of this Hessian, of the local quadratic approximation to the best fit. And it turns out that that local quadratic approximation will be the metric tensor in our differential geometry that's coming. So first, I need to explain to you that this is not just a biology problem. So here are the eigenvalues of the system I was just describing. They're roughly a factor of 3 apart, and they span 11, 13 orders of magnitude. This is a quantum wave function used in quantum Monte Carlo, our best, most accurate way of calculating electronic properties of small molecules, and it's sloppy. Here's the model of Cornell's particle accelerator, and you can change the knobs like mad, and only a few combinations of knobs really matter, and all the rest of them are basically unimportant for the behavior. So we have each of these has an enormous range of eigenvalues. They're roughly equal density in log, and they're all observed in a broad range of systems. And we've been spending the last 10 years trying to explain why this happens. And we have lots of other examples. Let me make a brief connection to physics. I talked to you about reductionism. We have various tools to deduce long wavelength behavior from microscopic complexity. One of them is like the diffusion equation, where the complicated rules of hopping and colliding at short length scales ends up with a beautiful differential equation. That's coarse graining. And the other one is the renormalization group that we use for critical points, showing self-emergence, emergence of scale invariance, like in the Ising model. And we can apply the same tools that we do to our sloppy models to find the eigenvalues about the behavior as you change parameters. We turn these into multi-parameter models by making your hops have different rates to different neighbors, or your bonds between the Ising model have different strengths for different neighbors. And then you can ask for the eigenvalues of the metric tensor about the Ising model, say. And as you coarse grain, and it's known that if you think about the microscopic model, then if you have perfect data about the microscopic model you're trying to fit, it's not sloppy. But if you're interested in long wavelength properties, sure enough, the known important variables, the diffusion constants and the average drift for the diffusion equation, or the temperature in the field for the Ising model, they turn out to be the stiff relevant variables, and the sloppy irrelevant variables peel off, and you get this nice hierarchy of eigenvalues. So next question. How does this tell us that the behavior is simple? You've got a few parameter combinations that matter, so you might imagine that means there is sort of a low dimensional structure in the behavior, and the studying that behavior brings us into differential geometry. So I'm going to call this a model manifold. It's not actually a manifold, but it's got some internal cusps and things that make it not a manifold. You could call it a manifold with boundary if you like. And these are the behavior in prediction space. So it's very simple model, the sum of two exponentials with two rates, theta 1, theta 2. And you can, and if you have data, you can fit it with this model, time series data, and then you'll get a best fit and these contours, just like I was talking about before. Now, obviously, we are more interested in models like 48 parameters, and with 48 parameters, I can't draw the pictures, so I'm going to start with 2. The predictions of this model, if I take 3 different time points and look for the 3 different predicted data points, for each set of parameters, there's a point on this surface. So these are the coordinates of the manifold. And as I take the parameters to infinity or to 0, I get finite values. So there are edges of the model manifold where one of the parameters hits infinity, one of the parameters hits 0, or the parameters happen to be equal. So behavior space, you have a manifold, a high dimensional manifold in a very high dimensional space. The parameters of the model are the coordinates of the manifold. The model boundaries are simpler models. And the metric tensor turns out to be just the least squares distance between the points on the manifold, just like the least squares distance to the data is the thing to minimize when you fit your model with the data. Final statement, I'll very briefly say, if I take an experimental measurement, say at time t2, it will slice this model manifold. The things that are consistent with the data now lie in a lower dimensional manifold, and that lower dimensional manifold will be of interest in a later discussion. The model manifold, the one I showed you, had this nice curvy structure, but when you go to high dimensions, it becomes a hyperribbon. I call it a hyperribbon in the analogy to hypercubes and hyperspheres. This is something that's got a long direction, a less wide direction, and then a very, very thin direction in the third direction. And just as we had a hierarchy of eigenvalues in the parameter space, so we have a hierarchy of widths. And in fact, the hierarchy of widths very nicely tracks the corresponding eigenvalues if you take the square root. Note here that the thin directions on the model manifold are the sloppy directions that had wide ranges of parameters giving the same behavior. And so you can go all the way to infinity along a geodesic in the sloppy direction, and you get very little change in behavior. Why is it a hyperribbon? I don't want to spend too much time on this, but it's basically an interpolation problem. If I have 3 or 4 measurements, then I can use interpolation theory to try to guess what the behavior is in between them. And every time I add a new data point, I get a tighter bound on the possible range, presuming that there's a bound on the nth derivative of the function prediction. So in this simple one-dimensional function of time, as opposed to a many-dimensional function of all control parameters, you can see that adding more data points gives you closer and closer ranges, and that corresponds geometrically to a hyperribbon. Every time I add a new point, I slice the manifold in a new direction. The fact that all my other predictions get thinner means this sliced manifold is thinner in every direction. I've sliced off the longest direction. I've got all the shorter directions. We have a rigorous proof of this hyperribbon structure using fancier linear algebra techniques, which has been recently published. Okay, now focusing on the goal of learning not how you get simple behavior out of a complicated model, but can you understand that simple behavior as a set of physical laws? Can you discover physical laws or discover the essential features that control this biological system or this accelerator by some kind of systematic procedure using these differential geometry ideas? And what I'm going to do is I'm going to now turn to not my work, but Mark Transtrum's work, in which he pulled this out of a hat. So the idea is, if you have a 48 parameter model of a systems biology problem, and you know that there are only 3 or 4 directions that seem to matter, shouldn't you just get rid of all the rest of the parameters? Let's make a simpler description. And I had 2 arguments. One was that the biologists wouldn't want a simpler description because they really cared about all those parameters. And the second is that if I take the sloppy directions, it looks like a random combination of all the parameters. And what Mark did is he was measuring the width of the model manifold by using geodesics. He would start in a sloppy direction, and he would go to the edge of the model manifold. Then he would be measuring how wide it is. And as he did that, he discovered, and now of course you can't tell where this is going to infinity in parameter space. When do you stop? And he learned that he could figure out that he was approaching the edge when this complicated eigendirection turned into something simple. That when only one or two parameters would go to infinity, then he knew that he was approaching the edge, sort of along a normal. And when he did so, if two parameters went to infinity, he would think about them biologically, and there would be something, typically not this, but I'd like to use this example. If I have a chemical reaction and I have a forward rate that's going to infinity and a backward rate that's going to infinity, and the logs of the two were both going to infinity at the same rate, which is what actually is happening here, then you can just replace the two by an equilibrium. That you've got something that's happening infinitely quickly, that reaction is in local equilibrium, and that just sets the ratio of the reactants to the products. And he not only found this for the sloppiest direction, but he would then simplify his equations. He would say, okay, I can take that limit. He had very flexible software that Ryan Gutenkunst had developed, so he could do surgery on his differential equation and run it again, do surgery on the differential equation, run it again, and he did so. So here's where he started with 48 parameters and 29 differential equations. And he ended up doing this procedure 36 times, reducing it to 12 parameters and 6 differential equations. Now, let me emphasize. First, notice I start off with some gigantic range of eigenvalues. I start off with a very complicated, messy system. Now, our cancer biology expert looked at this model and explained to us, after years of wise study, there was a central pathway down here that was shared between these two. There was a side pathway. Every bond here is a PhD, basically. And there's a side pathway that boosts the signal at late times. There's a negative feedback loop that turns the signal off after a little while. And then there was this side loop that he thought was going to be important, but we discovered wasn't, based on the predictions of our model and the subsequent experiment. When we simplified it, that's what's left. The central pathway, the side pathway, the negative feedback loop, plus one extra, you've got understanding from the simpler model. The original model had 48 parameters and all these differential equations. The new models, the differential equations are not that much worse. In fact, they're kind of nice. And there are only 12 parameters. And it's not a black box. A black box tells you this will happen when that happens. Here, each of these parameters are written down in terms of the microscopic model. So if your biologist wants to add a drug that changes KMD BRAF, they can do that. And we just figure out what that does to each of the thetas, and it'll tell us a prediction. This model fits the data almost as well as the original. That's why he stopped at 12. When he went to the next step, it stopped fitting the data very well. So this is Occam's razor in the best sense. Occam's razor is not always correct. We know that all the approximations we made here are not all valid, but they might as well be valid as far as we know from the data. Thank you very much. I like to think, okay, I'd like to think that the fact that the model boundaries are what well-trained neural networks are looking at is somehow tied to this. I'd like to think that machine learning and deep neural networks work because the world is simpler than we think. The world has some low-dimensional structure that these models are finding. And I'd like to think that we might actually be able to turn the results of the currently kind of oracular, here's the answer, don't ask me how I got it, that neural networks produce into something that is more comprehensible. Okay, thank you very much.